Hey YouTubers, it's Crafty Coder. I have an update on the single channel motorcycle or automotive PDU. This device allows you to control a single high current device like auxiliary lights or heated gear, and control the amount of current you push to it with a PWM duty cycle adjustment tool. And you get two signal inputs, a momentary switch that switches between 100%, 30%, and then a pre-programmed, well, not pre-programmed, programmed by you duty cycle, anywhere between 0 and 100. And it also has a high 100% override, so if you pull one of the signal pins to 12 volts or higher, it sends the unit to 100% duty cycle all the time. And you would use that if you were using aux lights, for example, and you wanted the aux lights to turn up all the way when your high beams were on. You could pause or tap that to your high beams, and then when the high beams are on, the auxiliary lights are on too. So right now I have the device actually running under test. I'm pulling about 8 amps through it at 13 volts, and which means we're burning, a lot of amps there, or a lot of watts, and we're making a lot of heat. But I'd like to show you, because the boards are new, these are the new high current boards, and I just built up one this morning to test it out, and it's looking quite good, so let's take a look. This is the new high current board. It's got 2 layers of 6-ounce copper. 6 ounce means if you had a square foot of it, of the foil, it would weigh 6 ounces. Now this obviously isn't a square foot, but that informs the thickness of the copper, and it's adequate to this task. The nominal max current for this device I've decided to set at 15 amps, though it would probably be fine at 20 or maybe 25. You're going to start to have some heat issues, so to be safe I would suggest never using a larger than 15 amp fuse, but if you want to try and you break it, well, that's on you, and that's fine with me. Alright, so here's the board under the scope. This one's mostly unpopulated. I just have a few parts on there to test the reverse protection. Power supply lives there. There's the programming headers. There's the microcontroller. There's all the signal inputs. And right there is the MOSFET and the MOSFET driver stuff. And then off the bottom, that's where all the wires go in and out. So that's the board. We could take a look at it up real close if we wanted to. Focus that in. Whoa, extreme close up. Yeah, so that's one of the parts there, very small. Gives you a sense of the size. We'll go smaller, bigger again. And a finger for scale, and there you go. Alright, so let's take a look at the device actually under test. There's the device built. All the parts on it. It's working very well. Here's the load. Well, one of the loads. I've got 2 loads on it. I've got a set of light bulbs and a 2 ohm resistor, totaling, like I said, about 8 amps. And this is quite warm. Let me pull out a thermometer and test it for you. I've got this thing cooking at about 170 degrees, 180. That's hot. That'll burn you. That's Celsius, not Fahrenheit, so that's in fuego. But we can try it on the MOSFET. and you'll see that the board is 25 degrees. And the table, let's test the table, is 22. So at half its rated current, apologize for the camera here, at half the rated current the board is up 3 degrees C, which pretty much means we are well within the capabilities of this device without any problems. It will be able to handle if you wire it up backwards, though we wish you wouldn't. And it's got a relay input so that you can have it off except when the bike is on. So there's no actual relay, but if you connect it to something that turns on when the bike turns on, you'll be able to have it switch on and not draw any current when the bike is off. That's pretty much it. We're going to get some of these built as soon as possible in mass, and work on the encapsulation part of this process and get them out for testing as soon as possible. So thanks for following along, and wish us luck. Take care.